Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare. This is my continuing feature on the Math Lovers book, a 3-volume series I wrote from 2019 to 2022 that's available on Amazon.com, both in Kindle and in paperback format. You can search for either of them if you type my name, David Tare, or the Math Lovers book. And you can purchase any combination of these 3 volumes or the whole set. Anyway, today I'm going to talk about Turing machines. This is a very important topic in computer science. I have to tell you what a Turing machine is. There's actually physical Turing machines that have actually been built, but it was meant as a theoretical device. Alan Turing came up with the concept of the Turing machine in 1936. I think you guys are probably familiar with Alan Turing. He was featured in the movie The Imitation Game that came out about 10 years ago. Very considered one of the pioneers of computing. Anyway, one of his many great accomplishments was coming up with this theoretical device known as a Turing machine. What a Turing machine does, I think you can kind of tell from this picture. It has a tape. That's what this white thing is on the top of the machine or in the back of the machine. And it has a printer. It'll print a symbol. In this case, just 0 or 1. This is a pretty simple Turing machine that can just print two different symbols, zeros or ones. Not only can it write a symbol, but it can erase a symbol. And it can also read a symbol. And it also has a different states, internal states that it goes into, a finite number of states, and that's all a Turing machine is. And it turns out the thing, even though it's a simple device, um, it turns out, and Alan Turing proved this, that anything in the world, any deterministic algorithm for computing anything you want, whether it's the space-time metric for some model of general relativity, could be something incredibly complicated like that. Anything that can be computed with any computer in the world, no matter how complicated, as long as it's a deterministic algorithm, given a given input always gives you the same output. It turns out that any computation like that can be done with a Turing machine. Pretty amazing. So the Turing machine kind of gets to the heart of computability. That's why it's a very useful concept, because Alan Turing basically outlined what was required for a computer. And every computer, I think pretty much every computer that's ever been built, at least since the mid 1940s, has been what's called Turing complete, meaning that it can, in principle, compute anything in the world. It might take an extremely long amount of time, but you can give it any program and it'll compute the result given any input. That's what I mean by it being a universally complete, Turing complete. There's another thing. I think this is just in my book. I'm just going to skip this slide. But here's basically this is a schematic diagram of the Turing machine, kind of a schematic diagram of the machine I showed in the first slide. So here's what a Turing machine does. Here's the tape, the long. You're supposed to imagine you have an infinitely long piece of tape or a tape of arbitrary length, so you never run out of tape. And what you do is it has this head that reads a symbol on the tape. You start with a blank tape, so the symbol it's initially reading is a blank, and then it starts in a particular state, and then depending on the symbol it reads, it can go into a different state, and it also has an instruction. It has to print a new symbol. Well, it doesn't have to, but it kind of does. I think 3 different things. So four different things. It reads a symbol, and then depending on the symbol and the state it's in, it can erase the symbol and print a new symbol, and then it has to either move to the left or to the right one space. That's all it does. And it just keeps doing this until it runs into instruction telling it to stop, halt. There has to be instruction that says halt, otherwise this thing could go on forever. So anyway, that's all a Turing machine is, and that's all it does. And there's also, another way you can represent a Turing machine is with a table. Maybe this is a little bit more intuitively, obvious as to what it's doing. So this is kind of like the program of the Turing machine. So you would start at, time zero, I guess. So, it might start in symbol zero, state S. Actually, the state slash symbol state is S0, and the symbol is the thing in this table. So say your first state is a state zero, and you're reading a zero, which could be a blank. What this is telling you, if that's the case, go to state one, print an X, replace the zero with an X, and R means move to the right. And then if you did that, then you're in state one, and you're reading an X, and then it just says do nothing. I think that means halt or something. I don't know what that means exactly, but you get the idea. This state and symbol table tells you exactly what the Turing machine is supposed to do given a given state and a given symbol. And you can also represent this graphically. Maybe this is even more intuitive. So here, I think this one's a little easier to trace. Suppose you start in Q0. That's just the notation here they're using for the state. You're starting on the left, and you're reading a zero. What it's telling you to do is replace the zero with a one, move to the right. And once you do that, then the arrow, you follow the arrow in the state diagram, you go to state Q1, and now what it's telling you to do is replace the one, which you just printed, with a zero, move to the right again. And you can keep following this diagram until usually there's a step that says stop or halt, because otherwise, like I said, it'll go on forever. But anyway, that's all a Turing machine does. And what else is remarkable about Turing machines? There's something called a universal Turing machine. This is a Turing machine that will simulate any other Turing machine in the world. And it's not even that complicated a machine. So in this case, the input has to be a particular Turing machine. And here we start with a state diagram of a particular Turing machine. So that's the input. That's the thing you're feeding into this universal Turing machine. And then the universal Turing machine will simulate this other Turing machine. It's saying, given this input, just do what this Turing machine is telling you to do. Because it already has these states in it. It's just, doing whatever that Turing machine's telling you to do. So Turing machines are very powerful. I think this is a really amazing result because, like I said, Alan Turing got to the heart of what's involved in any classical computation in the world. Yeah, and your laptop should be able to compute. Given the right program, your program's kind of like a universal Turing machine or a Turing machine. So, given any computer, doesn't matter what computer it is, could be your personal computer at home. Give it a program to calculate something, and run the code, and it'll work. It'll give the output. Doesn't say anything about speed, how long it's going to take. Uh, but it might take longer than the age of the universe. There are programs like that, unfortunately. And another problem with Turing machines is there's no way to determine whether a given Turing machine, given a given input, will ever halt or not. That's the halting problem. And I think Turing was also involved in that. It's also known as Church's thesis, the Church-Turing thesis. With Church and Turing, Church was another mathematician who lived around the same time. What they both proved was that the halting problem is unsolvable. I was talking about Gödel's incompleteness theorem. There are unsolvable problems in mathematics. Well, the halting problem is one of those problems. You can't, in general, given a given program and a given input, you can't ahead of time determine whether or not that program will halt. For all you know, it might run forever. Uh, which is kind of like Gödel's incompleteness theorem, I think. You might have a mathematical result which is unprovable. You can't prove or disprove it, but it still might be true. There's no way to check it, just like, in general, there's no way to check a given program with a given input. Most programs, simple enough programs, we kind of know they're going to halt and they'll give us the result we expect, but in general, we don't. So anyway, that concludes my video for today. on Turing machines. Thank you for watching. Long live math. I'll see you guys next time.